pure wavelength of electromagnetic radiation, it would be represented by a sine wave, and we've already mentioned, of course, electromagnetic radiation can be thought of, it's kind of hard to draw in 3 dimensions here, but it's a perpendicular oscillating electric field and magnetic field, perpendicular. And we said that the intensity of the wave is, this is the amplitude. If it were a sound wave, if you turned up the volume, you'd be increasing the amplitude. But it doesn't change the wavelength. And then we said the length of one cycle, we use the Greek letter lambda, and this is the wavelength, isn't it? So we're kind of reviewing here. And of course the wavelength can be in meters, nanometers, or whatever the dimensions of the wave are, but you have to be conscientious of the units of wavelength depending on the calculations you're doing. There's a kind of going back and forth between the PowerPoint. For electromagnetic radiation, we said that C is the velocity in vacuum is always going to be the same. It's 186,000 miles per second, but we use meters per second, 3.00. If it's to 3 significant figures, it's 3.00 times, as you see here, 10 to the 8th meters per second. And so if it's some other wave, of course, the velocity can be something else, but if it's electromagnetic radiation, the velocity is always this value. And we mentioned that it's equal to the wavelength lambda times the frequency nu. And the wavelength, of course, is the length in one cycle, and then the frequency is the cycles per second. And so, again, if we have the wavelength, if we have the velocity in meters per second, then we have to, the wavelength, lambda, has to be in meters per cycle, and the frequency is cycles per second. And we've mentioned this before, but sometimes we just leave out the cycles. And so if you're using this equation and you know the speed of light in meters per second, you may have to be conscientious of if your wavelength's in nanometers, for example, you would have to convert nanometers to meters if you're using this velocity for electromagnetic radiation. And of course this can be rearranged, and so the wavelength is equal to the velocity divided by the frequency. So if you know you always know the speed of light, and if you divide by the frequency, you'll get the wavelength. Or if you know the wavelength, you can divide to get the frequency. So that's fairly straightforward. But be conscientious here in this practice problem here. Notice how they had to convert. You have to look at the question carefully and review the practice problems we already did. But you have to be conscientious. If you're using the speed of light in meters per second, you're going to have, and you know the wavelength, you got to convert nanometers to meter. And just a little reminder of that. 1 nanometer is equal to 10 to the minus 9 meters, or 10 to the 9th nanometers is equal to 1 meter. Either one of these you can use if for some reason you have to convert from one unit to the other. Now, when we've talked about the amplitude of the wave, the wavelength, which is in meters or nanometers or whatever, the frequency in cycles per second, or sometimes it just has seconds to the minus 1 reciprocal seconds. The velocity of electromagnetic radiation, all of it is the same, 3.00 times 10 to the 8th meters per second. We talked about the fact that electromagnetic radiation has particle properties. These particles are called photons, and they don't have any mass, but they have energy. And the energy of a photon is equal to Planck's constant times the frequency. So the higher the frequency, the higher the energy of the photon. Or we could write it Planck's constant times the speed of light and divided by the wavelength. Okay? Either the larger or the higher the frequency, the higher the energy of the photon, or the smaller the wavelength. It's inversely proportional, the higher the energy of the photon. So high energy photons have high frequencies and small wavelengths. Low energy photons have long wavelengths and very small frequencies. Okay? Where we encounter them. Now, let's go back to our. And here it shows you the value. This is another point we need to take a look at. 6.626 times 10 to the minus 34. Planck's constant, and this course would be on the formula sheet I give you on Thursday. And this is in the units for Planck's constants in joule seconds. And keep in mind, a joule is a unit of energy or work. Work's a force times a distance. A joule is defined as a kilogram meter squared over second squared. And so, if you're using this equation here for the energy of a photon, and you're using this value here for Planck's constant in joule seconds, be conscientious that the wavelength has to be in meters. And so if it's given in nanometers, you got to change it to meters for it to be compatible with this value of Planck's constant. Okay? And then, of course, the frequencies in reciprocal seconds, so that's already compatible with Planck's constant. Okay? Something to be conscious, and maybe I should write this on the formula sheet. We also encounter this issue when we look at the Broglie wavelength. Now, just we're reviewing today, obviously. We already mentioned that here's the electromagnetic spectrum. The higher the frequency, the larger the frequency, the higher the energy of the photon, and then the shorter the wavelength. Generally speaking, as far as visible light is concerned, when we have frequencies greater than blue in the visible, these frequencies are higher energy. Ultraviolet, X-rays, and gamma rays are higher energy photons than any of the photons in visible light. And then when you get to frequencies less than red, infrared, microwave, radio waves, the energy of the photons goes down. Chemists use all of these things, by the way, to study matter, and so do astrophysicists. Astrophysicists study the microwave background of the universe. Astrophysicists look at X-rays produced by stars and nebulae, infrared, visible, ultraviolet, radio waves. These all tell us different pieces of information. In the chemistry lab, infrared, when a compound absorbs infrared photons, this causes higher vibrational levels. In the microwave, molecules in a gas phase have higher rotational levels. And then when you have absorbance either of visible photons or ultraviolet, as we've talked about, this causes electrons to go to higher energy orbitals. And then X-rays are used to analyze the three-dimensional structure of enzymes and proteins, and also elements in the crystalline state to determine the dimensions of atoms and molecules and so on. And so all these are useful in chemistry and physics. In studying the line emission spectrum of hydrogen, this was a very simple equation that resulted from studies of hydrogen when it was excited by analyzing all the different wavelengths of photons that were given off. Just to be reminded, if a photon, well, if an electron is in an excited state in a higher energy orbital, here's an electron, and sometimes chemists use an asterisk. If an electron's in a higher energy orbital and it returns to its normal, most stable state or a lower energy state, this change in energy here is exactly equal to the energy of the photon that's given off as a result of that. And this is the law of conservation of energy. Once you know the energy of the photon, well, then we already know the energy of photons, Planck's constant times the frequency. Once we know the energy of the photon that's given off, we can determine the frequency of that photon, and we can also determine the wavelength. Okay? It's conservation of energy, and we have for hydrogen, and this is just for hydrogen, the Redbird equation is extremely simple. The energy of an electron in any orbital in a hydrogen atom is just minus 1 times the Redbird constant, and the Redbird constant for hydrogen times 1 over the quantum number squared. And this is the first time that chemists and physicists introduced the idea of quantum numbers. So it was the first of the 4 quantum numbers that we learned about. And its values are just integers, 1, 2, 3, 4, etc. So you can use this equation, and the value of the Redbird constant is shown there, 2.18. Times 10 to the minus 18 joules, which is again a unit of energy, but this is the value of the Redbird constant. So if you have an electron in a certain orbital and it goes to a lower energy orbital, it's got to emit a photon that has the same energy as this change in energy. Now what about when an electron absorbs a photon? Well, it's the same thing, except backwards. Let's say an electron absorbs a photon and goes to a higher energy level. Again, this change in energy is exactly equal to the energy of the photon that caused it. Okay? This is absorbance of the photon when the electron goes from a lower energy orbital to a higher one. And then if an excited electron goes from a higher orbital to a lower one, it emits a photon. Emittance versus absorbance. For hydrogen, it's the same. You have the emittance spectrum is exactly the same as the absorbance spectrum, because the distance between the orbitals is the same, whether the electron's absorbing the wavelengths or giving them off, emitting them, okay? So that's actually a pretty simple equation, and again, this is only for hydrogen, so you need to make a note of that. It doesn't work for any other element. And so if you have, whether you have an electron going from an excited state to a lower one, or it's absorbing a photon and going from a lower one to a higher one, again, the change of energy, you can use this equation right here, it's just the energy of the electron in the final orbital where it ends up, minus the energy of the electron where it was initially. Okay? And if you know the quantum number for each of these levels, this is very simple. You calculate where it ended up, you calculate where it started, and you subtract them. And that's the change of energy involved, whether it's absorbance or emittance. Okay? Well, we can, instead of doing it, you can use this equation twice, once for each quantum number, if you know the beginning and ending orbital's quantum number, or you can combine them, and that's what we have here. If we, instead of calculating this twice for each value of n, and then figuring out the change in energy of those two orbitals, we can combine it. And again, this equation is exactly the same, really. It's just been rearranged slightly. But it's going to be, this time, the Redbird constant, this time it's positive, based on the order of the quantum numbers in the parentheses. 1 over n sub initial squared minus 1 over the final quantum number squared. And so instead of doing this, you can either do this twice, once for each quantum number, and subtract, or you could just use this. You get the same answer. Okay? Again, this only works for hydrogen. If you know this change of energy in the two electron states, then this change of energy is going to be exactly equal to the energy of the photon that was either absorbed when the electron went to a higher state, or that was given off when the electron went to a lower state. And once you know the energy of the photon, we already mentioned it, Planck's constant times the frequency, or Planck's constant times the speed of light over the wavelength. Once you know this, you can calculate the frequency of that wave or the wavelength of that wave. Once you know its energy, okay? Now I think next on your sheet is the Broglie wavelength. And again, I'm going to try to put together a formula sheet for next time that'll be the same formula sheet that's actually on the exam. The Broglie wavelength's mentioned here next, and de Broglie proposed, and it was experimentally demonstrated somehow, that if photons of light have both wave and particle properties, perhaps small particles of matter have both particle and wave properties. And this is called the de Broglie wavelength. And the particle has to have mass and velocity. And as it shows here, the Broglie wavelength for a particle, like an electron or a proton, some particle that actually has mass. It's the Broglie wavelength is, again, Planck's constant over the mass times the velocity. One thing about the speed of light, it's impossible to accelerate a particle faster than the speed of light. It's kind of like the end of the line. That doesn't necessarily mean chemists aren't looking for particles or trying to find particles that are already moving faster than light. And that's kind of a special area of research, perhaps. But if you have a body that has mass, you can't accelerate it any faster than light. And here we're talking about particles not of light. These are particles that have mass, like electrons and protons. And with a particle accelerator, you can get close to the speed of light, but you can't get faster than the speed of light. And so here we have u for velocity, because you need to know that. How fast is the proton or electron traveling to determine its de Broglie wavelength? It's a function of how much the mass of the particle is and its velocity. And this velocity is never going to be the speed of light. It's going to always be slower than that. And it could be pretty fast, but not the speed of light. And so we're writing u here instead of c, which is c is the symbol we've been using for the speed of light. But now we're talking about a particle. And don't forget that what unit does the mass have to be in if you're using Planck's constant? Does anyone remember? It has to be in kilograms. And if you need it, on the formula sheet, 1 kilogram, 1,000 grams. If you have the mass in grams, you're going to have to convert it to kilograms if you're going to put it in the equation with Planck's constant. Okay? And of course, the wavelength, of course, will be in meters if you use this equation for calculating the de Broglie wavelength. And the velocity has to be in meters per second, okay? To be compatible with the units of Planck's constant. Planck's constant units are joule seconds. This is the same thing as kilograms meters squared second squared. And then in the bottom, your mass has to be in kilograms. Your velocity has to be in meters per second. I think this is kilogram meters per second. And so now you see the kilograms can cancel, the seconds can cancel, and one of the two meters cancel, and your wavelength will be in meters. So if you're using this equation, you want to make note, the mass has to be in kilograms, the velocity in meters per second, to be compatible with joule seconds for Planck's constant. It's a simple looking equation, but you'd have to think about your units a little bit. Okay? Does anyone remember what the definition or the Pauli exclusion principle is?
No two electrons in an atom can't have the same 4 electronic quantum numbers.
Right. So when you have an atom, a multi-electron atom, which is any atom except for hydrogen, when you have 2 or more electrons in an atom, each electron has to have a unique set of 4 quantum numbers. There can't be 2 electrons in the atom that have the 4 quantum. At least one of them has to be different. Okay? Now, this is lead into quantum numbers of electrons and atoms, and let's remind ourselves of the rules for the quantum numbers. And I think I'm going to print this out and put it, include these pages on the exam as well. Here's the first one. The first of the 4 quantum numbers, N, is the principal quantum number, and you can think of it as energy level, and it has to be an integer, like 1, 2, 3, 4, etc. Here, this is just looking at 3 orbitals and 3 energy levels that are have the same value of L, and when L is equal to 0, we say those orbitals are s orbitals. But the important point here is when you go up from one energy level to another for the same orbital, it has an increase in radius. Next is the angular momentum quantum number L. And it's key here for a given value of n. So each L is dependent upon the value of n. L is equal to 0 up to n minus 1. So when n is equal to 1, there's only one possible value for L, and that's 0. Because 1 minus 1 is 0. So when n is equal to 1, L has to be 0. When n is equal to 2, now L can either be 0 or 2 minus 1 is 1. Okay? And as you go up in different values of n, you increase the allowed values for the angular momentum quantum number. N equal 1, the only possibility is L equal to 0. We call that an s orbital. N equal 2, L can be 0 or 1. When it's 0, that's going to be another s orbital. And when it's 1, you're going to have your p orbitals. When n is equal to 3, L can be 0, 1, or 2. When it's 0, that's an s orbital. When L is 1, those are p orbitals. When L is 2, those are d orbitals. And you get the idea. As the value of n goes up, the number of total orbitals that are possible goes up. And the orbitals is just a region of space the electrons occupy. The third quantum number, again, this, I think, I'll have this on the test too, these 4 slides. M sub L is the magnetic quantum number, and this is dependent on the value of L. So it's getting a little complicated. When n is equal to 1, there's only one possible value of L, and that's 0. Well, M sub L can go from minus L to plus L. When L is 0, M sub L has to be 0. In the second energy level, L can either be 0 or 1. When L is equal to 1, the values of M sub L are minus 1, 0, and plus 1. And these are the 3, what we call p orbitals. You have s orbitals, L is equal to 0 in all energy levels. So in the first energy level, there's an s orbital. In the second, there's an s orbital. In the third, and so on. They all have an s orbital. But you don't see the 3 p orbitals until you get to n equal to 2. You don't see the 5 d orbitals when L is equal to 2 until you get to n equal 3, and so on. And then the last one is easy compared to the other 2. When you get to the point of an orbital with a specific value of n, L, and M sub L, an orbital can only have up to 2 electrons total, and they have to have opposite spin, and so that's the 4th quantum number. Plus 1/2 and minus 1/2. So these I'm reviewing today, but these 4 slides, I'm going to put these on the exam. Okay? So you have a good feel for the 4 quantum numbers and the rules that govern the possible allowed values. Okay? Also, I think last time, I don't know if I have one with me today, but I gave you a periodic table. Is everybody comfortable using that periodic table to determine the electron configuration of any element on the periodic table? Does anybody have any questions about it? Let's just take platinum. Platinum has atomic number 78. So find platinum, atomic number 78, on your periodic table. Atomic number 78 here. And you can see what if you showed the entire electron configuration, that's 78 electrons. That's kind of busy. So this is a simpler approach. But what's the first thing we write down for the electron configuration for platinum?
Xe.
Okay, xenon is the nearest or the last noble gas
4D.
that's filled. And then, and this is platinum, atomic number 78.
4F.
14.
Okay, 4F, 14. When you get to the F orbitals, you know, there's S, there's 1S, there's 3P, there's 5D, there's 7F. The values from M sub L keeps going up when L goes up. But you don't encounter the 4F orbitals until you get to the fourth energy level. So that, and then all 7 of them are filled, aren't they? Because there's 14 electrons. And what next?
5D, 9, I think.
Okay, that looks like 5D9.
And then 6S1.
Okay. And one thing, you know, when you're working with the first 10 or 20 elements in the periodic table, electron configurations are fairly straightforward in filling orbitals. But when you encounter the d orbitals, there are elements that play tricks. Now, did everybody see how we did this one?
Yes.
Okay. And notice that platinum is a little unusual. It's got, if you look at the preceding iridium, it's 4F14, 5D7, 6S2. And they do magnetic studies on these elements to see if you have an unpaired electron that can result in a magnetic moment and so on. Let me just point out some glitches on the periodic table. Look at nickel 28, and then look at copper 29. And of course, for nickel and copper, argon is filled, and then for nickel you have 3D8, 4S2, but then you go to copper, it's 3D10, 4S1. There is some unusual stability in filling all 5D orbitals at the expense of the 4S orbital. So they get a little tricky. There's little glitches like that in the transition metals. But the main group elements usually are fairly predictable. Does everyone see how he came up with this electron configuration for platinum?
Yes.
Okay. Let's move it on here to the chapter 8. And you know, you have another copy of the periodic table, and you may want to get out. But 4 groups of the main group representative elements have names. Not all groups on the periodic table have names, but groups 1A, 2A, 7A, and 8A, actually, those groups have names, and they're part of the main group elements, which all end in the letter A. There's two main group elements, 1A and 2A on the left. And then we have the other main group elements, 3A through 8A on the right. What's the name of the group 1A?
Alkali metals.
The alkali metals. What's the name of the group 2A?
Alkali earth.
The alkaline earths. What's the name of group 7A?
Halogens.
The halogens. And then 8A?
Noble gases.
The noble gases. Location of transition metals on the periodic table. There are obviously these metals in the middle. On one of your periodic tables, those groups end in the letter B. Okay? In the center of the periodic table. Electron configurations of the elements in the periodic table, I've already given you the handout. You can ignore figure 8.1. I don't remember what figure that is. This is the handout you want to use. How do you determine the number of valence electrons for the main group representative elements on the periodic table?
Is that the same as a group number?
It's the same as the group number. Take your previous periodic table I gave you. Group 1A, the alkali metals, all have one valence electron. You now know that it's in an s orbital. Group 2A all have two valence electrons. You now know both of those electrons are in an s orbital and they have opposite spins. Group 8A, the noble gases, those are filled shells, and they're filled because they have filled p orbitals. They have 8 valence electrons, and they're unusually stable when there are 8 valence electrons. The 8 valence electrons really correspond to a filled s orbital and the 3 p orbitals. It's the filling of the p orbitals that ultimately results in the unusual stability of noble gases. For the halogens, there are 7 valence electrons. Okay? 2 of them are in an s orbital, and the other 5 are in p orbital. As you go each period on the periodic table, you're adding another set of s orbitals, p orbitals, and eventually d orbitals. The oxygen group, how many valence electrons does oxygen have? 6.
Yes. 6.
It's the same as the group number. And if you look at your the electron configuration, it's got the valence electrons are 2s2, 2p4. For the main group elements, this also shows you where the valence electrons are. We only talk about valence electrons for the main group elements. When you got d orbitals that are unfilled, the transition metals, they're not as predictable and easily predictable. The ions they form and so on. But the periodic table, the second periodic table it gave you, showing you exactly where the valence electrons are. How many valence electrons does nitrogen have? How many?
3.
Well, what group is
Oh, there's
nitrogen?
5.
5. How many does carbon have?
4.
4. You get the idea, okay? Again, that only applies to the main group representative elements, 1A through 8A, okay? Now, we can easily discern from the periodic table the likely charge of the ions that are formed by these same elements, because these main group elements can either lose electrons or gain them to form an octet in their valence shell. The first 2 groups, 1A and 2A, they lose valence electrons, and then the next shell of lower energy is filled. What is the charge that we predict for the metals, the alkali metals in group 1A?
Plus
Plus
one.
one.
Plus one. They're gonna lose that valence electron. And then the next shell is filled. If sodium loses one electron, it's gonna have the same electron configuration as a neon atom. Okay? So sodium, potassium, cesium, these lose one electrons, they have a plus one charge. What are charges the ions in group 2A?
2
Plus two. They lose two valence electrons, they lose two negative charges, they end up with a plus two charge. What about the halogens, group 7A?
Negative one.
Negative one. If they gain one more electron, they'll have the same number of electrons as the noble gas right next door. So if a chlorine atom gains an electron, it'll have the same electron configuration as an argon atom, but it'll have a minus one charge. Chlorine forms chloride, minus one charge. You might have fluoride in your mouth if you brush your teeth, it's got a minus one charge. What about oxygen, sulfur? What ions do they?
Minus 2.
Minus two. Nitrogen, phosphorus,
Minus three.
minus three. And that's nitride and phosphide, and that's kind of where it stops. Okay. What does isoelectronic mean?
The same number of electrons as the main group element configuration, or the electron configuration.
When an atom and an ion, or two ions, or whatever, when they're isoelectronic, they have the same number of electrons, and therefore the same electron configuration. Now, this doesn't apply to the transition metals. The transition metals, when they form ions, they don't necessarily have the same electron configuration as the other transition metal that has the same number of electrons. So this applies to the main group elements, the first two columns and the last six. And if you look at your periodic table, aluminum, if it loses 3 electrons, it has a 3 plus charge. After aluminum, of course, you've got magnesium, sodium. Magnesium, it loses 2 electrons. It has a plus 2 charge. Sodium, if it loses 1 electron, it has a plus 1 charge. All these have 10 electrons. They all have the same electron configuration as a neon atom. Let's go on the other side, on your periodic table. If fluorine gains an electron, plus an electron, you got fluoride. Oxygen gains 2. You got oxide. And then nitrogen gains 3. You got nitride. All of these and this, they're all isoelectronic. They all have 10 electrons, and they all have the same electron configuration. Okay? And they're main group elements. Okay? Oh, trends in atomic radii and trends in first ionization energy. Okay, we mentioned this before. We're looking at trends. Now, these are atoms, but generally speaking, when you go down a group, this is pretty obvious. We're adding, just going from hydrogen, going from hydrogen to lithium, we're only adding 2 electrons. But hydrogen only has a 1s orbital with an electron in it. Lithium has a filled 1s orbital with 2 electrons, and it also has a 2s orbital that has a greater radius. It's not at all surprising as you go down a group, the size of the atoms gets bigger, because you're adding more orbitals with more electrons. So that's intuitive, isn't it? But when you move across a period, the situation is a little different. When you go from lithium to beryllium to boron, and notice we're kind of skipping the transition levels here. We're just talking again about the main group elements. But as you go across, you're adding electrons to outer orbitals, but you're also putting another positively charged proton in there. Now we're skipping some of them here, but you're adding a proton going from boron to carbon to nitrogen, oxygen, and fluorine. And you don't see the trend here too well, but just generally speaking, when you keep putting positive charges in the nucleus, it pulls the orbitals in. There's more positive charge, there's more effective nuclear charge, and it has a tendency to pull orbitals in and make the atoms smaller when you go from left to right on a period, okay? Now, just generally speaking, if a metal loses electrons, well, they're the valence electrons. A cation is smaller than the atom from which it's made. On the other hand, nonmetals, when you add electrons, it's just the opposite. An anion typically going to have a larger size than the atom. You're adding something new to the outer shell. Here's trends in atomic radii, and you can see for different periods. The alkali metals are at the top here. They're the largest atoms in a period, and you get to the other end, the halogens, and they're much smaller. You're putting protons in the center, and it's pulling those orbitals in. Again, this should be intuitive. If you have these metals, like the alkali metals, you take an electron away, the cations are smaller. You're removing electrons from the outer orbital, they're going to get smaller. On the other hand, you take the halogens and you add electrons to them, they get bigger. Okay? Now here it's kind of showing you a lithium, when it loses an electron, forms a cation that's smaller. Fluorine, when it gains an electron, forms fluoride that's bigger. Now we're going to look at trends in ionization energy, and we talked about this a little bit. And they actually measure ionization energies besides the first. Generally speaking, for some elements, it gets harder and harder to remove an electron once you've already removed one, depending on the element, of course. But here's the trends of ionization energy for first ionization energy. And this should be also intuitive. Noble gases are the most stable elements on the periodic table. So it should be the most difficult to remove an electron from. And notice these trends. The noble gases are at the top of these peaks. The elements that are the most difficult to remove an electron from are the noble gases. And then the elements that it's the easiest to remove an electron from are the alkali metals, because they want to lose an electron and form a cation. Okay? So it's lithium, sodium, potassium, rubidium, cesium. They're on the bottom of these valence. Okay? And I think we finished this study guide here. One thing on these 2 chapters on the exam and the idea of electron configuration and this modern physics stuff and so on, the quantum mechanics is calculating orbitals as if you had an atom of the elements, but we've said this numerous times, but most of the elements in the periodic table don't actually exist naturally as pure elements. They combine with other elements to make compounds, and they can either do this by forming ionic bonds, which is fairly straightforward because you just need to take the atoms and form the ions, and you'll know the electron configuration of the ions. But when they share electrons, the situation gets a little more complicated, because when you have a water molecule, for example, there's an oxygen with covalent bonds to two hydrogens. These atomic orbitals we've been talking about don't stay the same, and they become molecular orbitals, and there's a couple of different theories we need to look at, valence bond theory and molecular orbital theory. And so the actual shapes of these orbitals we've been talking about changes when, especially when nonmetals form molecules. So the next chapter is on bonding, and we're going to see how these atomic orbitals change to form molecules.